Hi everyone. In this video, having learned a new definition for the limit, we now want to work through 3 examples to see how this new definition works in practice. To begin with, let's consider a function f of x, which is equal to x times sine of 1 over x. We want to ask ourselves what the limit might be of this function as x approaches 0. Now, before we begin a calculation, let's remember the first line of that new definition requires that the point we are taking the limit at, in this case 0, be an accumulation point of the domain. So the first question we have to address is 0 an accumulation point of the domain of f? Now, that begs another question. What is the domain of f? Now, in this example, I like starting with this example because it's fairly straightforward to figure out what the domain here is. You have a product of 2 functions. You have x and sine of 1 over x. X is a continuous function. It's linear, a polynomial. It's nice and continuous everywhere. Its domain is all real numbers. Okay. Sine of 1 over x is a little bit different, though, because here I have sine of 1 over x. Now, sine of any real input will be defined. So as long as 1 over x is defined, sine of that will be defined. So the only place I have an issue is where 1 over x is undefined, which is at x is equal to 0. So the domain of this function is the set of all real numbers other than 0. So I'm going to write this as the interval from minus infinity to 0, union 0 to infinity. Okay. So now that I know what my domain is, I can ask, is 0 an accumulation point of the domain of f? Well, what does that mean? What does it mean for 0 to be an accumulation point of the domain of f? That means I want to look at the deleted neighborhood for any radius r. I want to look at the deleted neighborhood of 0. I want to intersect that with the domain of f. And if this intersection is not empty for every value of r, then 0 is an accumulation point of the domain. Now, visually, if we draw a real number line here, my domain, and let's go ahead and label here, say here's 0. Let me label on here my domain. So my domain is going to be here in orange. But simply all real numbers other than 0. Orange here is the domain of f. And let me, in blue here, draw the deleted neighborhood of some radius around here. So here in blue, we would have, not showing up super well, so here in blue, we have the deleted neighborhood of radius r, deleted neighborhood of radius r around 0. Okay. Now, what is the intersection of these two sets? Well, just from here, we can see the intersection where they overlap is, in fact, the entire deleted neighborhood of radius r. These are all the points within distance r of 0 intersected with the domain of f, but the domain of f is all points other than 0. And so the intersection is, in fact, just the deleted neighborhood. So in this case, this is actually equal to the deleted neighborhood of radius r around 0, which is certainly not the empty set for any r greater than 0. And so 0 is, in fact, an accumulation point of the domain of f. So having established this, we can now say that we're in perfectly good shape to discuss the limit as x approaches 0 of this function x times sine of 1 over x. Now, again, this is not a guarantee that it exists. It simply says that the definition we learned last time can be applied to this situation. Okay? So now we have to ask ourselves, okay, we want to know what this limit is, and we want to prove that we have the right value for the limit. Well, our definition for the limit requires that we have an initial guess for the limit. So, for example, I need to prove that this limit is equal to some real number, and I need to have some idea before I begin my proof of what that number is. There are lots of ways you can do this. I could sort of look at this and think about what's going to happen as x goes to 0. So as x goes to 0, obviously this term here is going to be approaching 0. As x goes to 0, I'm not exactly, 1 over x is going to be going off to infinity, but it's sine of that, and sine is always bounded between -1 and 1. So I have something that's going to 0 times something that's bounded that probably tells me my limit is going to be 0. Um, I can also use technology, right? So I could graph this function. If you go into Desmos, it'll give you a perfectly good graph of this function or any other mathematical plotting tool. I've included here actually a plot that I created in Mathematica. So here's a plot of this function. And so if I sort of just examine this, right, as x is approaching 0, it does seem like my function values are getting smaller and smaller and approaching 0 as well. So my guess is that, in fact, the limit as x approaches 0 of f of x is 0. Oops, sorry. So that being my guess, let's actually see if we can prove that now. Okay, so I'm going to claim that the limit as x approaches 0 of f of x is equal to 0. Okay, so how do I prove this? So I need to show that for every epsilon, there exists a delta, such that whenever x is in the domain of f, and the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So to prove this, I'm going to take an epsilon greater than 0. Okay. Now, for that arbitrary epsilon, I want to show that I can find some delta where my definition works. So I'm going to tell you how to choose delta. But the only problem is I don't know what delta ought to be quite yet. Just put a box there for now. I'll come back once I figure out what it needs to be. So choose delta equal to something, some function of epsilon. So choose delta equal to something such that whenever x is in the domain of f and absolute value of x minus a, well, my a in this case is just 0, right? So whenever absolute value of x minus 0 is between 0 and delta, we have, all right, now I need to look at this absolute value of f of x minus L. I want to show that I can make this less than epsilon. This is where I'm going to need to choose what my delta is. So I first ask, okay, what is absolute value of f of x minus L? This is f of x. Well, for any x in my domain, f of x is just this function. This is x sine of 1 over x minus my proposed limit. Well, my proposed limit is 0. Okay, so minus 0. Okay, so I get that. Let's see. Here, I can just break this absolute value up here. Because this is a product, the absolute value of a product is equal to the product of the absolute values. So you can just write that. And now I look at each of these and I sort of think back to that reasoning I had before. I can make x really small, right? As small as I would like, in fact, right? So I can make x less than delta for any, I get to choose what delta is. So I can make x less than delta. Sine of 1 over x I don't have much control over, but I know that sine of anything is always between -1 and 1. That means the absolute value of that is always less than or equal to 1, right? So this here is less than or equal to this times 1, and I'm just dropping the 1 off. But the x I get to choose, and I'm going to choose it to be, oh, sorry. The x by hypothesis is less than delta. Absolute value of x is less than delta. And I get to choose delta. Well, I want this whole thing to be less than epsilon. Right now I have this whole thing as less than delta, so why don't I just choose delta to be equal to epsilon? Okay. And then if I choose delta equal to epsilon, this whole proof now goes through. Okay. And so I have proven my claim that the limit as x approaches 0 of f of x is equal to 0. Now, it's worth noting you could have used our old definition of limit to find this limit and to prove that it exists. Remember, our old definition of limit required that a function be defined on an interval containing, in this case, 0, except possibly the function isn't defined at 0. That is true here, right? In fact, this function is defined for every x value other than 0. So our old definition would work. What I want you to see here, well, A is just an example of how to use the new definition and the kinds of things you need to check. But we also see that we can also still use this new definition. So the new definition takes all of the old functions we could prove limits about. It still works for those and gives us valid proofs. We're going to see in some further examples that there are new types of functions that we would not have been able to consider before that we can now prove claims about limits of. Okay, so this is just a first example to get used to the mechanics of writing these proofs. Now, in our second example, we're actually going to take this example and just modify it ever so slightly. But we'll see that that slight modification it looks like a small algebraic modification, but it actually changes the behavior of the function quite a bit, quite substantially. All right, so let's look at a second example. And what you'll notice here is that I have just taken that function we had before, I've taken the square root of it. Okay, so now I have the square root of x times sine of 1 over x. Okay. Now, it's much harder, like if you start looking at this, right, it's much harder to make sense of what the graph of this might look like. I've actually included a graph here. So, what you'll notice, and this maybe isn't surprising, is that our domain now is rather strange, right? Because it's not just, I mean, you're still going to have issues at 0, because this will be undefined at 0. But now anywhere that this function was negative before is now no longer going to be in the domain of the new function. Anywhere where x times sine of 1 over x was negative is no longer in the domain of this new function, right? Because I don't get a real value out if I take the square root of a negative number. So I get this function that looks sort of like this. So you actually have your part of your domain starts at this value and extends off to infinity. Another part starts here and extends off to minus infinity. But then you get all these little closed intervals. So you get like this big, these infinite rays at the end that are in your domain. And then you get like pairs of like closed interval, closed interval, closed interval. But there are all these disjoint closed intervals that are getting smaller and smaller and smaller, but also occurring more and more frequently as you approach the origin. It's not even immediately clear here whether this is a function for which our new definition would apply, right? So it's not even clear that we will actually be able to say something about the limit of this function unless we can start to say something about the domain and accumulation points of the domain. Okay? So we could start by asking the question, what is the domain of f? It turns out that even that's a pretty tricky question to answer. And the reason it's tricky is you would need to figure out precisely for what range of x values this function is positive and negative. You're going to get a whole bunch of, again, disjoint closed intervals. They're going to have weird expressions. This is actually, it's not an impossible question to answer, but it's a difficult question to answer. And what I want to emphasize is that the definition of the limit actually doesn't require us to know what the domain is. What it requires us to do is to show that 0 is an accumulation point of the domain of f. So what I want you to see in this example is that we can actually show that 0 is an accumulation point of the domain without explicitly ever stating what the domain actually is. Okay, so in order to do that, let's sketch out what we want to do here. So I want to sort of make a claim, right? And my claim, maybe I'll be a little informal here. My claim is that yes, it is. 0 is an accumulation point of the domain. Okay. And so what do I want to show? Well, then I need to look at the neighborhood of radius r around 0, the deleted neighborhood, intersected with the domain of f. Now, what I can do, I need to show this is not empty. So what I want to do is I want to show that for any value of r, I can find at least one x value that is in this set and that is also in this set. Okay. So in order to do this, I need to sort of carefully step through a few different pieces. Okay. So the first thing I want to do is I want to show that I can find values where this is actually positive. Okay, so when will this be positive? So if I were to just sketch, maybe down here, I'll just sketch a graph of the sine function just for reference. This will be helpful as we start to think about this. So if I think about the sine function, right, look something like this. All right, my marker is drying out a bit. All right. And so these are multiples of pi, right? So this is pi, 2 pi, 3 pi. And what you start to notice is that sine, in order for sine of something to be positive, then you need your input value to be between an even multiple of pi and an odd multiple of pi. Even multiple of pi, odd multiple of pi. If it's the other way around, if it's between an odd multiple at the lower end and an even multiple at the upper end, sine of that thing will be negative. Okay. So what I want to do is, and I'm going to sort of sketch out some facts here first, and then we'll write a clean version of the proof. So sine of 1 over x will be greater than 0 when the input value, 1 over x, is between an even value, or sorry, an even multiple of pi and an odd multiple of pi. Okay. So for any little n for which this holds, that will work. And I can solve this for x. So if I take the reciprocal of all of these, that's fine, but then I have to actually flip the inequalities. So I actually get that 1 over 2n plus 1 pi is less than or equal to x is less than or equal to 1 over 2n pi. Okay. So for x values in this range, this will be positive. Okay. And notice that because of, again, the way I've done this, if I'm only thinking about n being, say, natural numbers, then x will also be positive. Okay. I can also, however, choose a capital N so that this is as small as I would like, right? So this is sort of a fact. The other fact is that I can choose a capital N in the set of natural numbers such that 1 over, so it's going to look a little strange at first, but then you'll see where this comes from. I can choose a natural number such that 1 over n is smaller than any real number I want. And the real number I'm going to choose here is going to be 2 pi r. So, right, this is one of the corollaries, or this is actually this is one of the corollaries of the Archimedean property. And so I can always choose a natural number so that 1 over n is less than any real number. So I'm just fixing that real number, where this r is the same r I have up here. Okay. And if I do that, that implies that 1 over 2n pi is less than r. So notice that what I'm doing here is I am, in fact, figuring out how to choose an n so that my x value, which will be less than 1 over 2 capital N pi, will be less than r. So my x value will be in here, but it will also be in my domain of F. Let's see now how we can put all of that together then to prove that 0 is an accumulation point of the domain. All right, so now to formally write this proof. So I'm going to take an arbitrary radius. Okay. And then what I'm going to do is I know that I'm going to choose a natural number, capital N, such that 1 over n is less than 2 pi r. So right, by having already established an r, this is now a fixed real number. I can always choose a natural number so that 1 over that natural number is less than that. And that implies that 1 over 2 pi or 2 n pi is less than r. Okay. Then I'm going to choose an x, a real number x, such that that x is between 1 over 2 to the 2 times capital N plus 1 pi. Okay. So notice what I'm doing. I'm setting up here that I'm choosing an x that will be in my domain, but I still need to do a little work to show that. So I'm going to choose my capital, or choose my x, my real value x, so that it's in between these two. And hence, so what does that tell me? That tells me if I chose x in this way, sort of undoing the work I did before, then 1 over x will be between, it'll look very much like a pi. 2n pi is less than or equal to x is less than or equal to 2n plus 1 pi, so that x times sine of 1 over x is greater than or equal to 0. Okay, so again, notice that this choice, since it's bigger than 2 times a natural number times pi, it's definitely greater than 0. So this x is greater than 0. And because 1 over x, sorry. Let me back up because I wrote the wrong thing here. Let me point at some different things. So let's start over. So x up here, right, is greater than this, greater than or equal to this, and this is strictly positive. Positive over positive times positive. Okay. Sine of 1 over x, well, because 1 over x is between an even multiple of pi and an odd multiple of pi, that's greater than 0. So I know this is positive, or I should say non-negative, because if they were equal, it'd be 0. So I've got something that is definitely positive. I've got something that is greater than or equal to 0. Their product must be greater than or equal to 0. Okay. Now, this tells me, the fact that this is greater than or equal to 0 tells me that that x value I chose is going to be in my domain. This is going to be defined. So x is in the domain of f. And the fact that x is less than or equal to 1 over 2n pi, and 2n pi is less than r, tells me that x is less than r and greater than 0, which tells me that x is in the deleted neighborhood of radius r around 0. So X is in the intersection because it's in both. And hence, that's not zero. Sorry, that's not the empty set. So what we've actually done is we have shown that zero has to be an accumulation point of the domain by showing that there's always at least one thing in the intersection of the deleted neighborhood of radius r around zero intersect the domain of f. We didn't have to fully describe the domain. We didn't have to fully describe the intersection of these two things. We just needed to show that for every r, and again, I did this for arbitrary r, so for any r, there is at least one thing in that intersection, which is all I need. I just need to know that that intersection is not the empty set. All right. So now we've done all this work. Now what we know is that zero is an accumulation point of the domain of f. So now that I know that zero is an accumulation point, I can actually go and talk about the limit. And what you're going to see is that once you know that you can use the definition of the limit appropriately, then the proofs are actually not much different than the proofs would have been for the old definition. It's simply that you need to be a little more careful to show that you can actually use that definition of the limit. All right, so what is the limit? Well, again, if I look at this, I sort of feel like, let's see, as x goes to zero, looks like even these ones that are bouncing up are bouncing up less. The oscillations are getting smaller, so it looks like maybe zero would be the limit. So my claim would be that this limit as x goes to zero of f of x is in fact equal to zero. Let's see if we can prove it. Okay. So what am I going to do? Usual trick, take epsilon greater than zero. Let epsilon greater than zero be given. Now I need to choose a delta. What's delta going to be? Don't know yet. Okay, leave myself some space here so that whenever we have x in the domain of f and let's see, 0 is less than absolute value of x minus a. Again, here both our a and our L are going to be 0. But whenever the absolute value of x is between 0 and delta, we have what? Well, I want to look at absolute value of f of x minus L. That's in this case going to be equal to now, you'll notice here I've dropped so L would be 0. Here's f of x. Here's L. I've dropped off the absolute values because if x is in my domain, then I'm going to get out a positive value. Okay, so I can just drop those off. Let's see, what is this? This is equal to the square root of x. Sorry, a little too far. Equal to square root of x. Let me actually be careful here. Is equal to the square root of the absolute value of x times the square root of the absolute value of sine of 1 over x. When you split these apart, you have to be careful because if these happen to both be negative, which could happen, right? They could both be negative, so their product would be positive. But then when you split them apart, you have to have the absolute values here. Okay. Now I look at this, and again, I play sort of the same game from before. I know that absolute value of x is less than delta. So I know that this has to be strictly less than square root of delta. I know that sine of anything is always bounded above by 1. Okay, so this is really just square root of delta times 1, so that can go away. Now I get to choose delta, and I want this to be whole thing to be less than epsilon. So why don't I choose my delta equal to epsilon squared, so that this will be equal to square root of epsilon squared. which will just be epsilon. And that concludes my proof. So as you can see, the actual structure of the proof, once I know that 0 is in fact an accumulation point, so I can apply this definition, then the proof is not much more difficult than the other before, right? It's showing that this definition can in fact be applied here because 0 is an accumulation point. That is the tricky part. Now, I do think it's tempting right here to stop for a second and go, maybe this is just like this sort of feels like a bunch of busy work, right? If it's not really sort of part of the justification of the proof, that like why am I bothering to check this? And the answer is that if we didn't check that our point was an accumulation point first, and we just applied this for any weird, function at any point, irrespective of whether or not it's an accumulation point of the domain, we would have some really unintended consequences. So just as a brief example of that, right, you can imagine, say, the following function. So imagine just like this function. Let's say this would be like square root. So this is square root of x, but I've shifted it 1 to the right. This would be square root of x minus 1. Okay. And think about the point 0. Okay. Now, 0 is not an accumulation point of the domain of this function. The domain of this function is the interval closed 1 to infinity. 0 is not an accumulation point of that domain. We can't apply our definition as it's stated. But imagine you tried to drop that condition. Then what could happen? Well, then you would want to say for every epsilon, there exists a delta. What I would do in that case is I would just choose my delta to be a half. I'd say, well, choose delta equal to a half. And then I would claim whenever x is in the domain of f and the absolute value of x is less than delta, which I'm choosing to be 1/2, then let's say I claim the limit. Here's the other thing. I could claim the limit as anything. Let me claim the limit as 17. So this would give me what? Square root of x minus 1 minus 17. I claim that. Okay. Now, here's the problem. This claim, if you don't know that your A value here is an accumulation point of the domain, like in this case, this claim is true. And you're going, wait, no, there's no way, right? So why is this true? It's actually what we call vacuously true. Why? There are no x values in the domain of this function such that the x value is within 1/2 of 0, right? There's no part of the domain of this function is within 1/2 of 0. So what happens here is you say, well, whenever this happens, this ought to be true. Well, that never happens. So logically speaking, this is always true. Whenever this happens, which is never, this happens. Okay. So you could put anything here and it would be, this whole collective statement would be true, right? So even propositional statements like, if the sky is green, then my name is Bob. That statement is true because the sky is never green, right? So here, because this is never true, there are no x values that satisfy this whole claim would be true. And that means that if we didn't require that this definition only work when we were dealing with an accumulation point, then we could have situations like this. And then we'd have to say that the limit of this function as x approaches 0 is 17, right? That would, of course, be nonsense. So what requiring that A is an accumulation point of your domain does is it guarantees that this is never the empty set, right? This guarantees that there's always some point within any delta you choose, right? There's always some point in the domain of f that's within distance delta of A. There's always at least one. It could be 1, 2, infinitely many, who knows, but there's always at least one, so that this is never, this whole proposition doesn't come up to be true because it's vacuously true. Okay, so this checking that it is in fact an accumulation point is actually very important. Okay. Now, in these first two examples, what we've sort of seen are functions that in the first case, right, it really wasn't that bad of a function. I mean, maybe the like actual definition of the function as x times sine of 1 over x was a little strange, but the domain was not that unusual. It was fine. Here we get one where the domain is quite a bit more unusual. Okay. And what we want to see in our last example is that these things, we can still have a lot of interesting behavior, even if our domain is like a nice closed and bounded interval, a nice compact set. You can still have sort of interesting limit type problems. So for this last example, let's look at the following piecewise defined function. So let t of x, so I'm going to define this piecewise. I'm going to break it up into cases depending on whether q is rational or irrational. So let's start at the bottom here. If q is irrational, if it's not rational, so it's irrational, then it's just going to give back 0. If x is rational, well, that means you could write it as p over q in lowest terms, right? So, and I'm imagining, sorry, that I'm just working on the interval 0, 1 here. I should have said here that t is a function from 0, 1 into r. So if t is between 0 and 1, I can express it, and it's a rational number. I can express it as p over q in lowest terms, right? So I'm going to express it as 1/2, not 3/6 or 9/18, right? And what I'm going to do is for that number p over q, I'm going to return the value 1 over q. Okay, so just to make sure briefly we understand before we go on, right? So again, t of 3/4 would be 1/4. This is a rational number, right? Since this is a rational number, I'm going to take this in lowest terms, right, and return 1 over the denominator value. If I had t of, say, 9/27, right? So I have to be careful. That's not in lowest terms. Lowest terms would be 1/3. The denominator is 3. It's just going to return that. If I had t of 2/3, that would be 1/3. If I had t of pi over 16, well, that's irrational, so it's going to be 0. Okay, so this is sort of how this function works. Now, this is a good example of sometimes, we often say like, oh, just, let's look at a plot in Desmos. Well, it's pretty hard to get a computer to plot. I was able to get at first I had Mathematica do this, and then I actually generated a plot in TIX in Tech to make this look a little nicer. But let's actually look at and understand the sort of plot of this function. So here's a plot of this function. Okay, so notice that I think the way to think about how you come up with this graph is to think about, so all the irrational values would just be 0. Okay, so all along here, there's like a whole bunch of points at 0, right? The whole bottom line is actually sort of covered up by orange points that are at all the irrational values, because all the irrational values return 0. All right. Now, you start sort of thinking about your rational values, but think about them in terms of their denominator when they're expressed in lowest terms. So if you start with the denominator 1, you have 0 over 1 and 1 over 1. They return the same value, right, because they have the same denominator in lowest terms. Then you go to the denominator 2, okay? Well, then you would have 0 over 2, but that's not in lowest terms. That would be 0 over 1. We've already got that one. Then you have, and this one's a little hard to see. If I put my hand up, it's a little easier to see. Then you have this point, right? So this is 1/2, returns 1/2. And then you would have 2 halves, but 2 halves is really just 1. We've already got that one. All right, that's all the things with our denominator of 2. Then I go to the denominator 3. Okay, well, what would I have then? I'd have, well, 0/3, but we've already done that. But I have 1/3. Okay, that returns that. And I would have 2/3, which would also return 1/3. So these are all the rational numbers expressed in lowest terms, which have 3 in the denominator. Then I would go to the fourths. Okay, now if I go to the fourths, I got 1/4. That's right here. I would have 2/4, but we've already done that one. There it is, right? That blue dot is 1/2. Right? We already did that one. Then I would have 3/4, which is right here. And then 4/4 is 1. We already have that one. Okay. And you keep doing this all the way down. So every one of these different colors is sort of another level of this chart going down. And it goes down all the way, right? So I've sort of stopped after like 11 or 12 iterations here. But right, this goes on infinitely. So you see these sort of trees branching off, it sort of feels like, and this goes all the way down sort of to the axis. Now, the first thing, if we want to even start thinking about limits of these, um, the first thing to sort of ask is, well, what even is like, what are the accumulation points of the domain? Well, actually, in this case, it turns out to be fairly simple because this function is defined for every x between 0 and 1, including 0 and 1. That is a closed interval. And what do we know about closed sets? They contain all of their accumulation points. So all of the accumulation points of the closed interval 0, 1 are all the points 0 to 1, right? Including 0 and 1. So we can definitely talk about the limit at each of these points. Now the question becomes, what is that limit? Okay, can we say something about what that limit actually is? The answer is hopefully not surprisingly yes, but we have to be a little careful about this. Okay, so let's sketch out how this might go. Now I'm going to make a claim here. Um, it's really sort of it's not this is not a very intuitive function, so it's hard to sort of say, oh yeah, I think I know what the limit might be. Um, the limit as x approaches a for any value of a. Okay, I claim that the limit as x approaches a of t of x is 0. Okay. Now that seems actually sort of wild, right? I mean, if we go back and look at, just for a second, if I switch back over here, right? Like, you're telling me the limit here at 2/3 is 0? I mean, that seems rather strange. Now, remember a couple things. One of the first things you might have ever been told about limits is, right, like limits don't care about what the actual function value is there. So actually, it's okay that this function has the value 1/3 here, right? I really want to know what's happening nearby. Okay. So, I mean, it seems strange that you'd be 0, but maybe it's not that ridiculous of a claim to make. All right. This is where you just have to sort of go step by step through the process. You may not always know exactly where you're going to be 4 steps from now, but you just I have a young daughter who watches the movie Frozen, and there's a song called "You Just Do the Next Right Thing," right? That's sort of what you have to do with these problems. Is you just well, what's the next thing I could do? Do the next right thing, right? And eventually that hopefully leads you to a correct proof. Okay, so proof. Maybe I'll switch back to this orange marker. So let's take epsilon greater than 0. Yeah, I'm going to need to choose a delta somehow. Don't know how yet. Oh, such that whenever x is in the domain of f, and now I need to look at this quantity, and I'm going to look at the quantity in absolute values t of x minus L. Now, what makes this tricky is t of x is piecewise defined. So probably what I want to do is I want to break this into 2 cases, right? So I want to say, well, what's going to happen if my x value is rational? And what's going to happen if my x value is irrational? Okay, let's see. So I'm going to sort of literally break up the rest of the sentence into 2 cases. So if, let's start with x is not rational, then what? Then t of x is equal to 0. And then, well, my absolute value of t of x minus L, well, t of x is just going to be, if x is irrational, t of x is just going to be 0. L is 0. That's just going to be 0, which is certainly less than epsilon. It doesn't matter what choice of delta I make, this will work. So, all right, this case is fairly easy, right? If my x is irrational, this is automatically going to be true. Now, the harder part, right, is what happens in the second case. Okay. And to understand that, I need to think about some things about irrational numbers. So let me sort of put a fact over here. So there are finitely many natural numbers Q such that 1 over Q, sorry, such that 1 over Q is greater than epsilon. Now, why is this true? This is actually a corollary of one of the corollaries of the Archimedean principle. So I know that eventually there will be some natural number Q such that this will be less than epsilon. And once I get to that Q that's big enough that makes 1 over Q less than epsilon, all the Q's beyond that will be such that 1 over Q is less than epsilon. So there can only be finitely many natural numbers leading up to that natural number for which 1 over Q is greater than epsilon. Okay. So what I want to do is I want to look at so then there are finitely many rational x values such that t of x, which is equal to 1 over q, is greater than epsilon. Okay. Now think about this. So there's only finitely many outputs of our function essentially that are going to be greater than epsilon. Now, your function is not one-to-one, so there aren't necessarily the same number. I mean, in general, just because you know there are finitely many outputs that satisfy something doesn't mean that there are only going to be finitely many inputs. But in this case, there will only be finitely many inputs that give you outputs of the form 1 over q. So for each 1 over q, there can be at most q distinct different inputs that give you that. So if there are, you know, if the maximum Q that works here, or if the number of these things that there are is 20, there's no more than 20 squared of these things, and that's even an overestimate. Okay, so there are only going to be finitely many x such that t of x is greater than 1 over q. Now this is important because I'm going to choose delta to be the minimum distance from A to one of these x values. Oh, sorry, I've gone too low on the board here. One of these x values. All right, and this is where you start to realize that sometimes it's actually not just as easy as filling in a blank, right? So here, what I'm going to do, right? Now, if you're writing this proof, if we're writing this proof up nicely in tech, right? If the point is to communicate a nice proof, right, and not to learn how to write these proofs, we would write this up much more cleanly. We'd insert this up here. But we're learning right now how to solve these problems. There's a second piece about writing it cleanly at the end. So if I was writing this cleanly, I'd say let epsilon greater than 0 be given. There are finitely many q such that this is true. Therefore, there are finitely many x in q such that this is true. Choose delta to be this. So that would all go in here, such that whenever x is in the domain, we get this. Okay, now how does this work in my last case? Then I say, okay, if x is in q, and t of x, So there's actually going to be sort of two cases within case two. If x is in Q and T of x is, actually, sorry, no, I don't need two cases. If x is in Q, then T of x minus L, so that's just going to be T of x. Okay. Now, I've chosen my delta so that I'm actually not in my interval, my delta interval around A, I have excluded all of the ones where 1 over Q is greater than epsilon. So here what I have is I just have 1 over Q, but my delta is close enough to A such that I have excluded all of the x values where T of x was greater than epsilon. So this is true since when x minus A is less than delta, T of x must be less than epsilon by our choice of delta. That's how we chose our delta. Okay. This is a rather strange proof. I mean, it's not strange, I guess, but it's very different than the other two we looked at, right? It's not one where we can calculate an explicit delta, but this is how we think through this kind of project, right? So now we've shown what happens if x is rational, we've shown what happens if x is irrational, and so we've covered all of our cases. Now we know that whenever x is in the domain of f and 0 is less than absolute value of x minus a is less than delta, then we will get absolute value of T of x minus L is less than epsilon, right, in both cases. Okay. Now, I mentioned in terms of the writing, we sort of mapped out here how this would work. I'm going to write up a nice proof of this and post it under the resources. So you can see, how I would weave all of these ideas together into a nice written proof, the kind of proof you might want to turn in an exercise set or in an exam. That concludes all the examples for today. Now that we have a number of examples built up, what we want to start doing are proving a few properties of limits, right? So we now really understand sort of the definition. We understand what are maybe the new weird things that can happen when I'm dealing with limits. And then we want to prove some properties. Once we have those properties, we then want to go on to discuss continuity, define continuity, and look at some of those properties of continuity, such as the intermediate value theorem and the extreme value theorem. So again, we will stop there for this video. And please, as always, let me know if you have any questions.